So in this question, they're asking us to imagine that the Milky Way galaxy can be represented by a disk with a certain diameter and thickness. So what we have done is we have drawn a disk, which is basically a cylinder. And of course, because it's a cylinder, it has a radius and a height. And our first step in solving this problem is to actually calculate the volume of this disk. Now remember, this disk is supposed to represent the Milky Way galaxy, so we're actually calculating the volume of the Milky Way galaxy, V subscript g. Now hopefully we remember that the volume of a cylinder is equal to pi multiplied by the radius squared multiplied by the height. Now, as far as the radius is concerned, we were given the diameter of this disk, so of course that means we're going to have to divide by 2. So you would take that diameter of 10 to the power of 21 meters and divide that by 2 to turn it into the radius. You would square it, and then you would multiply by the height of this disk. The question mentioned that the thickness was 10 to the power of 19. That is essentially the height of this cylindrical disk. So we have 10 to the power of 19 meters. You would punch that into your calculator. You would get the volume of the Milky Way galaxy, which turns out to be approximately 7.85 times 10 to the power of 60, and this would end up being in meters cubed. So that's step one, calculate the volume of the Milky Way galaxy. Next, we're going to look at that lone neutron star that was located about 3 times 10 to the 8th meters away from Earth. Here is a representation of that scenario. We have Earth, and then located at that distance of 3 times 10 to the 18th meters is that lone neutron star. Now what we have to understand is that we have a spherical region of space enveloping Earth. So we've drawn that little sphere with the dotted circle there. And within that spherical region of space that envelops Earth, we have that one neutron star. So it's going to turn out to be useful to calculate the volume of that spherical region of space that envelops the Earth. We can see that this would be the radius of the sphere. In other words, the distance from Earth to that lone neutron star would be the radius of this spherical region. So now we're going to calculate the volume of that spherical region. We need to use a different formula because the volume of a sphere is equal to 4/3 times pi times the radius cubed. Now the radius, again, is simply the distance from Earth to that neutron star. That distance was given to us as 3 times 10 to the power of 18 meters, and then we'll cube that. So when you punch this into your calculator, you're going to get a volume of about 1.13 times 10 to the power of 56, and then this is in meters cubed. So again, that's the volume of that spherical region. So now you're probably wondering, okay, we have the volume of the Milky Way galaxy, we have the volume of that spherical region. How do we relate these two numbers together? So that's what we're going to do next. And to do that, perhaps we can set up a proportion. And on the right side of this proportion, we're going to say that there is one neutron star within a volume of 1.13 times 10 to the power of 56 meters cubed. So again, that was from the previous picture. We saw there was one neutron star within that spherical volume. That's great, but on the other side of the proportion, we're going to say that there are X neutron stars within the volume of the entire galaxy, which we calculated earlier. That was that 7.85 times 10 to the power of 60 meters cubed. So this is the proportion we can solve, and that'll give us X, the number of neutron stars within the entire volume of the Milky Way galaxy. Now, how do we solve this? Well, we can cross-multiply, would be one way. So if you multiply this way, you're going to end up with 7.85 times 10 to the power of 60. I don't know what happened there. And then if you multiply the other way, you're going to get 1.13 times 10 to the power of 56 times X. And now to finish solving for X, just divide both sides by that 1.13 times 10 to the power of 56. That cancels it on the left side. When you punch the right side into your calculator, you're going to get about 69,444 neutron stars would be located in the entire Milky Way galaxy. If you need that in scientific notation, then of course what you can do is take this decimal point, move it over 1, 2, 3, 4 places. This would give you 6.94, we'll say. And since you moved it over 4 places to the left, you got to move it 4 places back to the right. So that means 10 to the positive 4. So that would be the scientific notation version of the answer. And then finally, if you're expected to round this, then you can round the 6.9 up to 10. So you would have 10 times 10 to the power of 4. And then you can simplify it even further, because when you multiply 10 to the 1 and 10 to the 4, you would add those powers together, and you would get 10 to the power of 5. So often we just want a very rounded sort of whole number estimate for the number of neutron stars. So that would be 10 to the power of 5 neutron stars. You can also say this number of neutron stars or even that number of neutron stars.